Here we're continuing our study of vertex algebras, and we're finally ready to look at the structure of the non-negative products. So if you recall, in some previous videos we looked at the structure of the negative products in terms of this thing called the normally ordered product. And then we also looked, in the case of a commutative vertex algebra, everything works out pretty nicely. So that's the previous video. So now we want to finish off looking at some of the basics and look at these non-negative products. So what I mean is like the zeroth product, the first product, and so on and so forth. And this is really good news because just after this video, our next video can be our first big juicy example, which will be the vertex algebra associated to one free boson. In other words, the Heisenberg vertex algebra. So before we get into it, let's recall like our definition. This isn't quite careful enough to be a super precise definition, but it's close enough for us at the moment. So a vertex algebra is a vector superspace. So that means it is a direct sum of even components and odd components. The even components live in V0 and the odd components live in V1. And we endow this vector space with infinitely many products. So that means we've got infinitely many ways to multiply an element A and an element B from this vector space. And those infinitely many products are indexed over the integers. And we denote this multiplication with just a subscript. So we've got A sub n B, that's like the nth multiplication between A and B. And then we've also got a special vector, which is generally called this blackboard bold 1, or there's some other notations for it that I've mentioned in previous videos. This is known as the vacuum vector. It is an even vector. And then we also have two important linear maps. One is called the vertex operator. The vertex operator is part of this thing called the state field correspondence, which we'll talk about later after we have some examples under our belt. And it is a map from V to the ring of formal Laurent series whose coefficients are endomorphisms from B. So that sounds really scary, but the idea here is you take our products and instead of thinking of them as products, we think of them as linear maps associated to the left vector. So instead of thinking about this as the nth product between A and B, we think of this as the nth linear map attached to A, and then that is acting on B. So this is essentially the same thing. And we write this vertex operator down like this. So we've got y, a, z. So that's going to be the sum over all integers, a sub n, z to the minus n minus 1. And this vertex operator is a very important tool for understanding all of the products, as we've seen in the past videos. And then we've also got this other linear map called T, which is the translation operator. Okay, and then we've got these three main axioms that are satisfied, and I've kind of combined a couple in this case. But we've got the vertex operator of the vacuum vector is just the identity map. So in other words, the negative first multiplication is the identity map, and all other multiplications are 0 when you're dealing with the vacuum vector. Then we have the minus first multiplication of A with the vacuum is A, so that's called the creation axiom. And then we've got A sub n 1 is equal to 0 if n is bigger than or equal to 0. So here we want to think about this vacuum as being like the lowest energy state. And so anything with a non-negative mode here, that's what we call these sometimes, would raise that energy state, but we're or lower that energy state, but we're lowering it past the lowest energy. So there's nothing down there. And then next we've got this rule involving the translation operator and the vertex operator. So the commutator of T with YAZ, that's the same thing as what we get if we compose T inside of Y. In other words, we're doing Y TAZ, but that's the same thing as taking this formal partial derivative of the vertex operator with respect to Z. So that's cool. And then next we've got this thing called the locality condition. And that says for all A and B and V, there exists some natural number n such that z minus w to the n times the commutator of these vertex operators, so YAZ, YBW equals 0. So again, this is called locality. And I want to point out that often we use this notation, YAZ equals A of Z, and we can actually define the commutator as follows. So this is for homogeneous elements. In other words, elements that are either only in V0 or only in V1, but this extends linearly to non-homogeneous elements. So we've got the commutator of AZ and BW, so that's going to be AZ BW minus -1 to the parity of A times the parity of B, BWAZ. So if they're both in V1, this actually turns into like an anti-commutator, but if one of them is in V0, then that is a commutator because we've got -1 to either the 0th power or the first power. Okay, so now here's the big idea behind vertex algebras, and that they endow vector spaces spanned by objects like this. So we've got some sort of set of as simple vectors as we can get, and those simple vectors are these A upper 1 to A upper K. Maybe we've got a huge infinite list of them, and we've got a span of those vectors continually acting on each other and then acting on the vacuum at the end. So we've got A upper 1 M1, A upper 2 M2, all the way up to A upper K MK acting on 1, and here these MI's are integers. And this extra structure that is endowed by the notion of a vertex algebra is natural in some sense. So it has ties to like something happening in the physics world or something. Okay, and then how we want to think about this is a polynomial-like ring with non-commuting variables. So we saw this in the past. At one point it was just a polynomial ring, so everything commuted, but then you can also have like some sort of universal enveloping algebra type structure of a Lie algebra, so you have some sort of non-commutative polynomial ring. But the important thing here is we know the commutation relations. So you might say, well, why do we need this extra structure? But we need this extra structure because at the moment we do not know how to deal with the associativity here. In other words, we don't know how to deal with AMB, so combine that first and do the nth multiplication of that object with C. So with all of the kind of classical structure built into these types of rings, we don't know how to deal with objects like that. That's why we need this extra non-classical structure. And what we would like to be able to do is write some object like this, which is associated incorrectly, in terms of objects like this, which are associated correctly. So here I've written A, P, B, Q, C, and here we're thinking about the associativity coming from right to left versus here where we're going from left to right. So naturally, the things in our vertex algebra are written in this format. So anything in this format is really like non-standard way of writing things in the vertex algebra, so we'd like to reassociate it down to something like this. And so the answer to that is we want to use the associativity formula for this vertex operator. And it's kind of a lot, but it turns out that it breaks down into two cases depending on the positivity or the negativity of our mth product here. So we've got this vertex operator of AMB, so in other words, that vector, Z, is equal to the residue with respect to W. So what that means is just the W to the -1 coefficient of this expansion. And now we have W minus Z to the M, AWBZ. And you might say, well, what do we do with this object right here when M is a negative number? Well, we're going to expand it in non-negative powers of the second entry. So in other words, in terms of Z. So we've got this residue and then minus -1 to the parity of A times the parity of B, the residue with respect to W of minus Z plus W to the M, BZAW. So in other words, here we're expanding in terms of non-negative exponents of Z. Here we're expanding in terms of non-negative exponents of W. There's some sort of complex analytic interpretation of this in terms of expanding within a region inside and outside of a certain circle. And then I want to point out, and this is maybe a really good exercise, like for instance, if a textbook was being written, this would be a really good exercise, and that this definition is equivalent to this piecewise definition. which says that if m is negative, then this is equal to 1 over minus m minus 1 factorial, and then the normally ordered product of the minus m minus first derivative of a with b. And I want to point out we defined this normally ordered product in a previous video, so check that out if you need to. So this is not new, but writing this kind of like in terms of this thing right up here is new. But what is new is this thing down here, which is the non-negative products. And it turns out that we have y a sub m b z for a non-negative m is equal to this monstrosity. So we've got the sum as k goes from 0 to m of the binomial coefficient m choose k. Then we have minus z to the m minus k. And then we have the commutator of a sub k and then b z. And this might look problematic because we're just writing this in terms of a commutator, but that's actually preferable given this red fact up here that we know commutation relations. So we don't know associativity relations just yet because those are not baked into kind of the classical definition of the spaces that we are endowing the vertex algebra structure on. But we do know commutation relation. So essentially what we're doing is we're taking this kind of new type of object and writing it in terms of these old types of objects. And I want to point out that if A and B are homogeneous, in other words, they're either in V0 or V1, then that's defined like this thing over here. But if they're not, then we can split it up using linearity. Okay, great. So now I'm going to go ahead and get rid of this, and then we're going to look at some examples. Okay, so now we're going to look at our first example. And I'm going to say the example is to reduce this object. So we've got the 0th multiplication of A with B. So we combine that first, and then we take the nth multiplication of whatever that is with C. And we want to reduce that to something which is associated correctly. So in other words, associated from right to left. So let's go ahead and jump into it, and we'll use the vertex operator along with these definitions that we had on the bottom of the last board. So I want to point out that A sub 0 B in C, that's going to be the coefficient of z to the minus n minus 1 of the vertex operator A0 BZ, and then evaluated at C like that, just by the definition of the vertex operator, which we have over here. Okay, good. But now what we can do is use the definition that we had on the last board for this 0th multiplication composed inside the vertex operator. And that's going to give us something like this. We'll have the coefficient of z minus n minus 1 of, we'll have the sum as k goes from 0 to 0, because here our product is, well, it's most definitely a non-negative product, but remember the upper part of that sum is whatever that non-negative product here. Here it's just 0, so we've only got a one-term sum. And then we have 0 choose k minus z to the 0 minus k, so that's just going to be minus k like that. And then finally, we have A, K, B, Z, and then we need to evaluate all of that on C as such. Okay, so let's see what we get. We only have a one-term sum here, so this is pretty easy to write down. This is going to be the coefficient z minus n minus 1. We'll just take k equal to 0. So 0 choose 0 is 0. That's easy. And then we've got minus z to the 0 is just 1. So that leaves us with A0, B, Z, C. Great. So the only place we see Z's is in this component right here, this field B of Z. So that means we can bring this coefficient inside just like that. So that's going to give us A0, and then we have the coefficient of Z minus N minus 1, B, Z, C. But now, again, kind of by the definition of the vertex operator, and then using the fact that we often write this down here, we know exactly what this is. This is going to be the commutator of A0, and then we've got B sub n Z. C, I should say. Like that. But now we know that the commutator goes like this. So we'll just assume that these are homogeneous elements. Otherwise, we could extend it linearly. And this is going to be A0 Bn minus -1 to the parity of A times the parity of B of Bn A0 evaluated at C, like that. And now we can go ahead and push this through, and we'll get A0 Bn C. So that's associated in the correct order. Notice we're associated from right to left. And then we have minus -1 to the parity of A parity of B, Bn A0 C. So if we look at the extreme left-hand side, we've got something that is not associated correctly. Over here on the right-hand side, we have something that is associated correctly. But I'm not going to stop there for this one, because there's actually a really good and nice view for this zeroth product. It plays a special role. And we can see that by adding this term to both sides of the equation. So that's going to give me something like this. We have A0 Bnc equals, so we've got this thing over here on the left-hand side. So A0 Bnc, like that. And then after moving this over, that's going to be plus -1 to the A minus to the B. So that's the parity there. And then we've got Bn AOC. AOC. Okay, so now let's go ahead and notice that this really looks just like the product rule. So you might say, well, how does this look like the product rule? Well, if I put some parentheses in here that are invisible, but they are assumed, we'll see it immediately. So notice that this is A0 on this product Bnc, but then over here we have A0 on B, and then A0 on C. So let's just compare that real quick to this derivative rule from Calculus 1, which says we have f prime g plus fg prime. Notice that it's essentially the same thing with the addition of this parity thing. And so this actually makes this zeroth multiplication something called a derivation with respect to all of these nth products. Okay, so I'm going to clean up the board and we're going to look at a bigger example. We're going to finish this video off with a little bit bigger of an example. So I want to reduce this thing, which is associated, quote, incorrectly, AMB, and then do that product, and then do the nth product of that with C. And I want to do this where M is some arbitrary non-negative integer. We're going to do this using the definition that we had on the first board for the like kind of associated vertex operator, along with, you know, just some combinatorial tricks. So let's see what we get here. So we'll have A, M, B, N, C. So that's going to be the coefficient of Z to the minus N minus 1 of the vertex operator A, M, B, Z, and then C. But then from the first board, we know what this vertex operator is. So it's just the problem of finding the appropriate coefficient of this vertex operator and then reducing it to something that's a little bit usable. So we can go ahead and rewrite this as the coefficient of Z minus N minus 1. Then, like I said, we know what this vertex operator is. It is the sum as K goes from 0 up to M. And then we have this binomial coefficient, M choose K, and then we have minus Z to the M minus K. And then after that, we have A sub K, and then B of Z, that whole vertex operator. And then we're going to hit that on C at the very, very end. And I want to say that although these are like some heinous equations, they really do impart this natural structure on these like formerly classical objects. And also there are some like geometric interpretations of this that make sense as well. So it's not like we've just defined this thing kind of as gnarly as possible just for fun. There are important reasons for that, which maybe we'll touch on in future videos. Okay, so now let's simplify this a little bit. So I can bring this coefficient operator inside here. I can bring this power of z inside here as well, and I can split the power of z off from the power of -1. So let's see what we get for that. We'll have this sum as k goes from 0 to m. We have -1 to the m minus k. We've got this binomial coefficient m choose k. And then next, we've got the component operator a sub k. And then that is commuting with the coefficient of z minus n minus 1 of z to the m minus k times the vertex operator b of z. In other words, y, b, z. So like that. And now you can really do a number of things to kind of figure out what this is. You could maybe absorb this z to the minus m minus k into the coefficient and change the exponent down there. But any way you do it, you'll get kind of the same thing. So let's see what we get. We'll get the sum as k goes from 0 up to m. And then we'll have -1 to the m minus k. M choose k. Like that, and now we'll have the commutator of ak with, so again, we just have to figure out which component is pulled out of this, and it is going to be b sub m plus n minus k. So I'll let you guys play around with that if you need to check that, but that's what you get, and then you get all of that times c. And then recall, this is going to be the commutator just as defined over here. So let's go ahead and assume that we've got homogeneous vectors. In other words, they are either only in V0 or only in V1. They can be in different ones. A0 could be in V0 or V1. B could be in A0 or V0 or V1, but they're not made up of a combination of even and odd things. If they are, we can extend it linearly. Okay, and then that allows us to write this as the sum as k goes from 0 to m of -1 to the m minus k. M choose k. And then next, we're going to have ak b m plus n minus k c. And then -1 to the parity of a times the parity of b. And then b m plus n minus k a k c. So we've got something like that. So now if we go ahead and look at the extreme left-hand side and the extreme right-hand side, we have a way of writing something which I've called incorrectly associated. Maybe it's like non-canonically associated in terms of things that are associated canonically. And then I want to point out that if you go on Wikipedia and maybe look at something called Borchard's identity, which is of course going to be in Vertex Algebra textbooks as well, this is essentially what we have created here. This is Borchard's identity. Up to a small reindexing. So it won't look exactly the same on Wikipedia, but it will be equivalent up to this reindexing. So again, this is a really important identity for the whole theory of vertex algebras. Okay, so like I said before, this video was important, so now we have an idea for all of the products, the negative products and the positive products, and actually puts us in a really good position to jump into our first juicy example, which we will in the next video, the vertex algebra of one free boson, in other words, the Heisenberg vertex algebra, which is an important example of something called a free field vertex algebra, of which there are 4 main free field vertex algebras, and we'll be looking at all of them. Okay, that's a good place to stop.